All right, so we're going to go ahead and kick into chapter 15, more on probability. These are some of the probability rules we're going to use. Okay, now we're going to do some of these in class. The idea is that you get the notes here. We practice lots of problems in class. So we get a better feeling for how to apply these rules. So number one, a little bit of review. Sample space is a set of all the possible outcomes from some random phenomena. For example, I'm rolling a die. Well, I could get the numbers 1 through 6. That's my sample space. Alternatively, and part of this is everything in the sample space is itself a simple event. So what I'm saying is, my 1, that's a simple event. I could get a 1, I could get a 2, or I could get a 3. Each one of those is a simple event. The sample space are all the simple events that could occur. Now, how can I make sure I've got everything, all possible outcomes? How can I make sure I've accounted for all of them? Well, let me tree diagram. So for example, let's say I'm going to toss a coin and then roll a die. Well, if I toss a coin, that's my first step. There's 1 and 2 possible outcomes. I could get heads or tails. Well, then I roll a die. So I could get a heads followed by anything on number 1 through 6. Same thing on tails. I could get that tails and then followed by number 1 through 6. So by completing my tree diagram, I can follow the branches and make sure I've accounted for all the possible outcomes. By doing my tree, every decision has a certain number of outcomes, and on each decision I've listed them. So I can make sure I have all of the possible outcomes have been accounted for. Working down the list, I could even work down my list. Now I could get heads. That doesn't want to write. We'll try that again. I could get heads and a 1. I could get heads and a 2. Heads and a 3. Heads and a 4. Heads and a 5. Heads and a 6. I can continue down. So by following my tree branches, heads and then a 1, by doing this and making sure I put all my branches, following each one of my branches down, I can make sure I've accounted for all possible outcomes. So I haven't forgotten anything. Or if I'm just trying to make a list of all the possible outcomes, I could forget something. So instead we do a tree. Trees are especially helpful when I'm talking about multiple events, about the chance of getting a heads and a 1, or a heads and a 5. Anytime doing multiple events, a tree diagram could be especially useful. Now, the thing is, how many different outcomes were there? Well, we can look, there's 12. The way this works is called the fundamental counting principle. If I have m different choices at decision number 1, n different choices at decision number 2, then together I can say I have m times n total choices. For example, in this case, we said I could have gotten heads or tails at my first decision. So that gives me 2. The die, there's 6 different things I could get. Then I have 12 possible outcomes from the fundamental counting principle. You've used this before. It's come up in other classes. Algebra 2, they use this, but we're going to bring it up again. For example, let's talk about Al Capone has 3 kids. How many different outcomes are there with respect to the gender, the sex of the children? Now we're going to use the simplest cases, what's most common. Well, first thing is, I list my decisions. I have 3 decisions. Each child is a different decision. The first child, well, they can be boy or girl, male or female. Second child, so I got to multiply. I have a second decision. Again, keeping it simple, male or female. Now my last choice, so another multiplication. I had 3 decisions, so 3 times, I'm going to multiply all 3 numbers. 2 times 2 times 2, I have 8 possible outcomes. Okay. So that's our fundamental counting principle. Every time I give a decision, that's another number I'm going to have to multiply by. Now let's make sure we understand this about what constitutes an outcome. So in this case, what do you think about what would be an outcome? Well, we said the first child, so we have a first decision, could be boy or it could be girl. But then I have a second decision for each of these. It could be a boy or a girl, boy or a girl. Third decision, boy, girl, boy, girl, boy, girl, boy, girl. Now I can follow the branches of my tree. So coming down this topmost branch, that would be boy, boy, boy. Working straight down a list. How do I get to that end point? Well, that's boy, boy, girl. Or I could have had boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. 8 possible outcomes. Those are all the possibilities. So I can make them in a list just like that. But I use my tree to help populate my list. Alternatively, I could say, well, what about the possible number of boys? This is a different sample space. It's not just a possible birthing, including birth order. How many number of boys could I have? Well, could have 3. Could also have 2. Well, this is still 2. 1, 2, 1, 1, 0. So I could have 3 boys, I get 2 boys, 1 boy, or 0 boys. So my sample space for number of boys is 0, 1, 2, 3. And just looking at that, it looks like my probabilities are not equal for all those. These are different outcomes. I can only get 3 boys one way out of 8. Same thing for no boys. There's only one way out of 8. But if I want to know about, what about getting 2 boys? Well, I can look at my tree. There's 1, 2, 3. 3 ways out of 8. So these aren't all equally likely, but some events are equally likely. Let's keep going. Okay, just another way how I can fill in my sample space. Use a tree. Now, if everything in the sample space has the same chance of happening, then the chance of that event is 1 out of n. 1 out of how many different outcomes are there. So in this case, we said it wasn't happening, but if I was rolling a die, well, it's 1 out of 6. Chance of getting a 1 is 1 out of 6. Chance of getting a 2, 1 out of 6. Chance of getting 3, 1 out of 6. Chance of getting 4, 1 out of 6. So on and so forth. But again, not all simulations, and in fact, most of the time, we don't have equally likely outcomes in situations or in simulations. And we had to deal with that when we did experimentation and simulations. We had something happen 70% of the time they'd make a basket. That's not equally likely outcomes. So my tree, I'd have to do some things in there to help me answer questions about it. Now, the chance of any event is the sum of the probabilities making up that event. For example, what's the chance of me rolling a 2 or a 3? Well, my chance of getting 2 is 1 out of 6. My chance of getting a 3, 1 out of 6. So I add those up and I get 1/3. But these are disjoint events. I can just add them up that way. There's no overlap. I'm not counting anything twice. So disjoint events, we get a simple addition rule. Just add the probabilities together. The question is, I'm going to say about this one. What about getting a number larger than 2? Well, that's like getting numbers 3, 4, 5, or 6. So I just add the probability of each of those together. 1/6 plus 1/6 plus 1/6 plus 1/6, 4/6. That's equal to 2/3. What I used to do is a complement. So right now I said, what's probably rolling a number larger than 2? So the complement is kind of like, it's almost like the opposite of that. If it's not larger than 2, then it must be less than or equal to 2. Well, I could get a 1, and I could get a 2. If I can subtract that from 1, and what's left over is the rest of the probability. So in this case, 1 minus 1 over 6 plus 1 over 6, or 1 minus 1/3, that gives me 2/3. Sometimes the complement can be easier to calculate, okay? But we still end up with the same answer. Now, Chapter 14 gave us a lot of restrictions. We could only use those rules if events were independent. Another rule, we could only use if the events were disjoint. But I got a couple more rules. Now, we're just going to call them events A and B. So the general addition rule, I can always use the general addition rule. Okay, I can always use, whenever I want to say what's the chance of the probability of the probability of A or B. Whenever you see that union, that means or. Probability of A or B. Let's make probability of A plus probability of B minus the probability of both of them happening at the same time. Now, when they're disjoint, by the way, you get this on the formula sheet. Okay, you will get this on the formula sheet, exactly how it's shown. Now, this works because if A and B are disjoint, then A and B was 0. So this is still the same as what we had last time, where we said we had this rule if they were disjoint. Yeah, because that last one's going to be 0. But I can always use this general addition rule. I can always use this top rule. Just sometimes A and B is going to be 0. Right? Now, let's think about this. What's the chance that when one card is drawn from a deck, it is an ace or it's red? So let's think about it. First off, are those disjoint events? Well, no. There's 2 red aces in a deck of cards, the ace of diamonds and ace of hearts. So instead of just show what I'm doing, I'm going to use that formula. I want to talk about the probability. So probability of getting ace or red. Using our formula, well, that's going to be the probability of an ace plus the probability of red minus the probability of ace and red. Of course, I've made it a little bit easier to see. I want to show my work. So that's what I'm going to do. Probability of ace or red equals the probability of ace plus probability of red minus probability of ace and red. So now I want to substitute in these values. So chance of getting an ace. Well, there's 4 aces in a deck of cards out of 52. So that's my chance of getting an ace. How about a red card? Well, there's 13 diamonds, and there's 13 hearts, and that's all the reds, so that's 26 out of 52. And then I want to subtract the overlap. Well, there's 2 red aces. So that's it. We'll get 28 out of 52. Moving on. We can also use a Venn diagram to show this. Okay? We had our aces. Now the catch was using a Venn diagram. Here's my aces. All my aces are in here. So there's 4. 2 here, and 2 of them over here in the middle. That's 4 total. Red cards. There's 24 that aren't aces, but 2 that are. So here's my Venn diagram. So the chance I get an ace or a red card, I'd add all these up. 28 out of 52. Now, I don't really recommend using a Venn diagram to answer these, but we can use a Venn diagram if it's provided to answer them. Now, we also have the general multiplication rule. We had the special multiplication rule if events were independent. And that one, we said A and B was equal to the probability of A times the probability of B. But that only worked if the events were independent. So how are we going to deal with it if the events aren't independent? It's going to look very similar. We're still going to have the probability of A. But instead of just being multiplied by B, if we're multiplied by A, we're saying A must have happened. So we're going to say the probability of A times the probability of B, and that vertical line means given. The probability of B given that A happened. This rule I can use every time. Because if they're independent, we've said it before, if they're independent, knowing A happened doesn't change the probability of B. So if they're independent, that should be true. Probability of B given A should be equal to the probability of B. So given shouldn't change anything if they're independent. But if they're not independent, those two things won't be equal. So let's say I draw 2 cards without replacement. What's the chance that both of them are aces? So first thing is, are the draws independent? Well, I'm drawing without replacement. So I have deck cards, pull one out. I set it to the side and draw another card. That second card is going to be different based on the first card. The probability of getting certain types of cards is going to change. So no. So I have to use this rule. I have to use the general multiplication rule. So let's see how I do that. So I want to show my work. Probably both cards are aces. Well, the only way that happens, the first card had to have been an ace. Otherwise, they're not both going to be aces. So the second card, well, what's the chance it's an ace given the first card was an ace? Because if both of these don't happen, then I can't get 2 aces. So what is the chance the first card I get is an ace? Again, think about a deck of cards. There's 4 aces out of 52 cards. Now I want to look at my second probability. What's the chance of me getting another ace if the first card was an ace? Well, I pulled 1 card out, so there's only 51 cards left. And if the first card was an ace, well, there's only 3 left. So I'm going to have 4 over 52 times 3 over 51. I multiply it, I'm going to get 12 over 2652. Now I want to tell what my answer was. I want to think about what I'm doing, I want to show my work, and then tell my answer. The probability that 2 randomly selected cards are both aces is 12 out of 2652. Tell my answer in a nice, clean, clear sentence. So independence. Again, we said events are independent if the outcome of one doesn't influence the probability of the other. We double check our independence with that same test. We figured it out actually a minute ago. A and B are independent if the chance of B given A is just equal to the chance of B. Knowing A happened doesn't change our chances. Alternatively, it means the exact same thing. Let's think about this for a second. If the chance of one doesn't change the other, I could rewrite this. I have B given A. What about A given B? No. It should look just like that. Knowing B happened shouldn't change the chances of B. Or knowing B happened shouldn't change our chances of A. Okay? So the probability doesn't change, then it doesn't change. They're independent. They're not affecting each other. Now, conditional probability. We have a couple rules we get to use. Okay? The chance of B given A happened. Well, this is how we solve it. And you get this on formula sheet too. It's the probability of A and B happening divided by the chance of A. And the way we got this, we just manipulated that first equation a little bit. Let's go back and take a look. Go way back here. All we did was manipulate this equation a little bit. I've got A and B divided by A. Well, I'm dividing both sides by the chance of A. B given A is equal to A and B divided by A. All we've done is manipulate that equation. So you get that equation on the formula sheet. It's being given to you. We're just going to manipulate it a little bit. If A and B are independent, okay, if A and B are independent, the chance of B, we get this. A and B are independent. Then B given A is just a chance of B. So if we did that, well, those A's are going to cancel. The probability of B is equal to the probability of B because they're independent. So it holds. The formula is showing us that it works. Again, you get that on the formula sheet. So we want to practice. We're using that formula sheet to help us answer some questions sometimes. Of course, I can reverse where B and A are, but that means I need to do it on both sides. Reverse A and B, I'm going to reverse A and B. Every time I see it in A, I turn it into a B. Every time I saw a B, I turn it back into an A. It can work either way. I just have to move where the letters are at. Okay. So let's say I draw a card and I look at it. I tell you it's red. So I pulled a card and it's red. What's the chance it's a heart? First thing is we got to think about this. We're going to think, well, was the card selected at random? Yeah, it's selected at random. So I want to show our work. So I want to find what's the chance it's a heart, but we know it's red. So it's not just chance it's a heart given that it's red. Well, that's going to be equal to the chance of heart and red divided by the chance of being red. Well, what's the chance the card I draw is a heart and it's red? It has to be both. Well, good news is all the hearts are red, and there's 13 of them. So I know my numerator is 13 divided by 52. It's going to be 13 over 52. My denominator, chance of getting a red card. Well, half the deck is red. So it's going to be 26 out of 52. So if I set it up, I flip my denominator, multiply, because, that's how I like to do that. 13 over 52 times, and I flip my denominator so I can multiply. They cancel. 13 over 26, and that simplifies to 1/2. So just want to use that formula, just moving things around, asking ourselves what are certain probabilities. Okay. So again, though, we still need to tell our answer. If a randomly chosen card is red, the chances of heart is 50%, 0.5, or you could say 1/2. Remember, probability, we normally got 4 decimal places. Come on. So what's the chance the card is red given that it's a heart? Well, think about it. What am I being asked for? Chance it's red given it's a heart. So I know I got a heart. I'm looking for probability of red given it's a heart. Well, we've been saying this. We're going to use my formula. That's probability of red and heart divided by probability of, think about it. I want you to think about it for a second. Probability of getting a heart. So now we're just going to solve this. Put in our probabilities. What's the chance of getting red and a heart? Well, that's 13 out of 52. Chance of getting a heart, 13 out of 52. Overall, we simplify and cancel. We're going to get 1. Well, it makes sense. What's the chance of getting a red card given you got a heart? Well, all the hearts are red cards. So it's going to be a 100% chance. Be 1. So tell your answer. If a randomly chosen card is a heart, it is certain to be a red. It will be red. Whereas a 100% chance it will be red. All these different ways could have told the answer. Now, disjoint. Disjoint events cannot be mutually exclusive. Remember, disjoint means if one thing happened, the other one couldn't. There's no overlap. If they're disjoint, they can never be independent. So this is kind of a quick thing because every now and then you'll see a quick question on a test. You might be able to answer right away. Are these two events disjoint? Let's think about for a second. For example, how about red card and a spade? Are they independent or are they mutually exclusive? Well, they're disjoint. There are no red spades. Since they're disjoint, they're also mutually exclusive. It's the same term. They're mutually exclusive. If you get a red card, you did not get a spade, and vice versa. How about red card and ace? Are they independent or mutually exclusive? Well, let's think about our test. Our test was if the probability of red card given I got an ace, if that was equal to the probability of a red card, then they were independent. Knowing that you got an ace didn't affect the probability. We solved this before. Probability of getting red given it was an ace. So that's how we're going to check it. We're going to test for independence. Red given as an ace was 2 out of 4. 2 of the aces are red. Chance of getting a red card overall, again, 1/2. Half the cards are red. So, or 26 out of 52. If I simplify these, I get 1/2 equals 1/2. Those are the same. So they are independent. How about face card and king? So again, we're going to set this up. We need to know is probability of face, given it was a king, equal to the probability of face. So if I get a king, what's the chance to get a face card? Well, it's 1. Probability of getting a face card. There's 4 kings, 4 queens, 4 jacks. So I have 12 cards out of 52. Those are not equal to each other. I put one too many lines on that. Let's try that again. Put one too many lines on that. They're not equal. Since they're not equal, they're not independent. But are they disjoint? Okay, face for even king is not equal chance of face. So they're not independent. Next question is, are they disjoint? If I get a face card, is it even possible to have gotten a king? Well, yeah. The fact that it's a chance of 1, face card given king, they're not disjoint. So it's neither. All 4 kings are face cards, so they're not disjoint, but they're also not independent. They don't have to be one or the other. Disjoint events are never independent. But just because it's not independent, that doesn't mean there's going to be disjoint. So you actually have to run the check to check for independence. So we were going to fill this out in class, and we did in one of the classes. We went through males, how many wore jeans, how many were not wearing jeans. So I'm going to make up a couple numbers. Okay, and we're going to use these when we're going through here. We're going to say we have 10 males in jeans, 5 wearing some other type of pants, to give us 15 total. Female, we're going to say we had 8 wearing jeans. Well, we'll say 10 something else to give us 18 total. I'll fill up the rest of my totals, 18, 15. If I add these up, 33. Now we'll use these numbers on the rest of the examples. So you're going to take a moment, copy this down so you have it as we're going through the rest of the examples. Pause the video if you need to. Get these numbers written down. I may come back to this page, or I'll just copy things down from it. Okay. Hope you got it. So, what is the chance that a male was wearing jeans? Now, the wording of the question matters quite a bit on these. What is the chance that a male wears jeans? So in this case, we assume we're pulling a male at random. So we're looking for the probability they wear jeans given they were male. So use our formula. Probability of A given B. So that's the number of students that are male and they're wearing jeans. In this case, that was 10. So my numerator is going to be 10. And total males, we had 15. I could simplify it. We have 2/3. Try it again. What's the chance that someone wearing jeans is a male? So what's the probability someone wearing jeans is a male? Well, that assumes we're pulling randomly. We're asking what's probably their male given they're wearing jeans. A given B. So it's still going to be A and B for the top. Students are wearing jeans and male. We said that was 10. But this time it's divided by the total number wearing jeans, which is 18. So we'd get 5/9. So again, the way the question is worded is going to change the numbers you have to use sometimes. So you have to pay attention to the wording of the questions. Let's go ahead and try another one. Are being male and wearing jeans disjoint? Being male and wearing jeans disjoint. Well, no, we had lots of guys who are wearing jeans in my example. So they're not disjoint. How about sex and attire independent? Are sex and attire independent? Well, we know our test for that. Oh, sorry. If the probability of male given jeans is equal to the probability of male, then they're independent. So probability of male given they're wearing jeans, well, that's 10 out of 18. And probability of male was 15 out of 33. Now I can put these in the calculator and simplify. In fact, I can do a little bit right now. 15 divided by 3 is 5/11. These are both even, so I can divide them. 5/9. First off, I can tell you right now I'm done. 11 and 9 are both prime numbers. These are not equal. Since they're not equal, they are not independent. If they're independent, they'd be equal. So no, they're not independent. Now again, we use tree diagrams. Let's say 100 boys, 100 girls, asked if they ever made a purchase over the internet. 30 of the boys, 60 of the girls said they've made these kinds of purchases. If one of the teenagers picked at random, what's the chance they made a purchase over the internet? So what I need to do is fill out my tree diagram. I've got my decisions. First thing is, I had 100 boys, 100 girls. So, well, so my first decision I'm going to use is my gender. Now in the boys, let's see. Okay. I'm going to divide it up. If I pick a person at random, the first thing I'm figuring out is, what's the chance to get a boy or a girl? 50-50. Had 100 boys, 100 girls. Next question I have is whether or not they buy something over the internet. So my next decision, have they bought something? And we remember the probabilities were not the same. 30 of the boys bought something. 60 of the girls bought something. So for boys, they either bought or they didn't buy. Girls bought or they didn't buy. For the boys, 30% bought. For the girls, 6% bought. How about didn't buy? Well, they either bought or they didn't, 70% and 40% respectively. So I've almost got my tree complete. The way I find out the probability as I go down the tree is I multiply as I go down the branches. So if I know the probability someone is a boy and they've bought something, I have to multiply 0.5 times 0.3. If I know the probability someone is a boy and they haven't bought, 0.5 times 0.7. Girl who has bought, 0.5 times 0.6. Girl who has not bought, 0.5 times 0.4. If I do all that, I get all my individual numbers. So finally, I want to say, what is the probability someone has made a purchase over the internet? Well, I'm only talking about there's only two groups, boys who've bought and girls who bought. There's no overlap between these. You can't get to this if you're a girl. You can't get to this one if you're a boy. These are disjoint events, so I get to just add them together. So I'm just going to take 0.5 times 0.3 and add it to 0.5 times 0.6, and we're going to get 0.45, or 45%. Then you have to round it off. There's only 2 decimal places on these. And that's it. That covers all of our questions. I do have this one here, give you a little bit to think about. Okay. If you chose one of these numbers at random, you chose an answer at random, what's the chance you'll get this question right? 25%, 50%, 60% chance, or a 25% chance? You can think about this one. Okay. This is not homework. It's not extra credit, but something to think about. Maybe you can Google it and find the answer. But don't forget the homework. Chapter 15. It was questions 1 through 10, 12 through 15. Whoa, that got all messed up. Try that again. Woo. Okay. 12 through 15 and question 29. Also, you need to attempt that handout I gave you. Again, these handouts I'm giving you, some of these are going to turn around. You might see them again. Okay, so again, one last time, chapter 15. Questions 1 through 10, questions 12 through 15, and question 29. There is no web work on this one. So I look forward to seeing you soon. Make sure you send me questions, come by after school, and look forward to seeing you soon.